All right, module 3.3.2, we're going to be finishing up with potassium and a little bit about the micronutrients. So we've talked about nitrogen and phosphorus and a little bit about sulfur previously. And so potassium has the least impact on the environment. So nitrogen having the greatest impact because there are so many different transformations that happen that we can get losses from several different of those processes and transformations. Phosphorus is going to also be important in environmental pollution with our eutrophication, but potassium has very little. I'm not saying that it doesn't have, that it has none, but it has very little impact or negative impact on our environment. So it's not toxic. There's not a lot of eutrophication. So potassium is really kind of benign, or it doesn't really, cause any major problems. Even though it doesn't cause any problems, it is very important to plant and animal nutrition, as it is important for these enzymes that are basically for metabolism. In plants are going to be photosynthesis, some breakdowns of some sugars. They're going to lower the cellular osmotic water potential and kind of go into water loss or kind of water maintenance. And so for me, when I think about potassium, it's going to be like the electrolytes. And so when we've been playing some sport or we've been working very hard in the day, what we want to do is, we've lost a lot of water. We want to add that potassium back so that it will regulate some of the, it'll kind of hold on to some of that water so that we don't lose it to sweat or transpiration. Same thing in the plant. So as I mentioned, it does play a role in photosynthesis and protein synthesis. It's important for sugars. But what I also like to think about potassium as is kind of like the immune system of the plant. And so it is going to allow that plant to adapt to some of these environmental stresses. And that's mostly going to be in the form of the water management or, kind of the water regulation. So drought tolerance and winter hardiness. It also plays a role in resistance to disease and pest tolerance. And it's important for making sure that, those sugars and the colors of the flour, the flavor that we get in our vegetables and our fruits are going to kind of be related to potassium. So potassium is very mobile in the plant. And when it's mobile in the plant, we are going to see that on the older leaves first. So that's going to be the edges of our older leaves, kind of like nitrogen, are going to die first. But one of the things that, one of the easiest ways to determine the difference between potassium deficiency and nitrogen deficiency is you'll start to see this curling up, right? You'll start to see this kind of burnt edge. And this burnt edge is because most of the water in that edge is going to the center of the leaf, or it's just not there anymore. So you can think about if you dried a leaf out and took all the water away, then it's very crumbly. And so that's the reason why you will see this on the edges with that burnt part, because there's just no more water there. And once it dries out, it just crumbles. So potassium availability, it's in a lot of our mineral structures. And when it's in a mineral structure, it is unavailable. We have non-exchangeable potassium in those secondary minerals, and those are not readily available, so slowly available. We have exchangeable potassium on the soil colloid. That is readily available, so that's cation exchange capacity. And then finally, we have potassium that is in the water, and that is also readily available to the plant because the plant is going to take up that water and it gets all of the nutrients that are within that water. So there's not a whole lot going on for this potassium cycle. We apply fertilizers, it's taken up by the plant. It's either adsorbed or desorbed to the soil colloid and these different minerals. Like you don't even have one of these. Just to understand that it's really a mineral thing, and that as those minerals break down, we get potassium released into the soil. One of the main things to note about potassium is that we can have a lot of plant uptake and removal greater than what the plant needs. And so we call this luxury consumption, where the plant will continue to take up that nutrient whether it needs it or not. So remember that the plant will take that up through being desorbed off the soil colloid and taken up through active uptake, or that potassium can come into the plant through passive uptake, which is in the water. So the plant didn't specifically seek out to find that potassium. It was in the water as the plant was taking that water up. Only about 1 to 2% is readily available. Most of that is going to be adsorbed to the soil colloid. And, we just kind of hoping that we get some release of that fixed potassium in some of those primary and secondary minerals. Some things that are going to affect that fixation are, obviously going to be our soil colloids. Does it have a high CEC? Is it strongly adsorbed to that soil colloid? Excessive lime is going to change. Remember that if we have acidic soils, we have a more positive environment because we have a lot of hydrogen plus ions. But if we have if we have an alkaline environment, then we have more hydroxyls or OH negatives, and that can also influence how much that potassium is held to that soil colloid. And we have that right here with soil pH. Some things to understand about potassium management is just how often you apply that, how much did you apply, how much was available in the soil, and then how much did you remove from the field. So you don't necessarily have to apply a lot of a lot of potassium if you already have enough potassium in the soil. Again, this is where soil tests come into play, because then you know what you have and you can save a little bit of money by not having to apply that potassium. Okay, so moving into micronutrients. And so we have, previously we talked about most of these, at least our N, P, and K, sulfur, and now we're going to talk a little bit about our micronutrients. And there's not a whole lot to go on with this, especially not for the soils class. We would talk a little bit about micronutrients in soil fertility. But there is this trend where we're starting to look at micronutrients because we're trying to, find every little bit of that production system that we can tweak to make that efficient. And we want to make sure that we have enough micronutrients because they're important for enzyme production and some of those other metabolic processes that kind of take place that you don't really think about. And so we don't need these in high concentrations. That's why they're called micronutrients. And if we don't have enough of these in our plants, then we might also run into some human and some animal deficiencies, such as manganese. So a little bit about how we describe these plant nutrient levels. I guess this is going to go back to talking a little bit about law of diminishing returns and where we have hidden hunger, and when we need to apply and when we expect to see a response. So if a plant is deficient, then that would mean that the element is low enough to severely limit yield. This goes back to Liebig's law of the minimum. So you could have all the nitrogen, you could have all the phosphorus, potassium, sulfur, calcium, magnesium. If you're deficient in boron, you're only going to get as much yield as that boron deficiency will allow. We have critical range, and that is where that plant nutrient is just below the yield response, or is just below the level that if we apply fertilizer, we will see a yield response. If the plant nutrient level is sufficient, then obviously we don't need to apply more fertilizer. It's sufficient. If we apply more fertilizer because we think that if one is good, then two is better, then we can get a toxicity. And if the plant has too much of a particular nutrient, we have this toxicity. Now, not only have we spent more money on the fertilizer, but we're also going to decrease our yield, which decreases our return on investment because we over-applied this fertilizer that now caused us to have a yield decrease instead of a yield increase. And then, as I mentioned with potassium, we have this luxury consumption where it will continue to absorb those nutrients beyond what is needed for that maximum yield. So here our plant is deficient. This is the critical concentration such that, if we apply fertilizer somewhere here, we expect to get a yield response. If we apply enough fertilizer, we will see a yield response from that. If we were to apply fertilizer here, we would probably not recognize that benefit. And if we over-apply certain elements, then we would start to have a toxicity. Which brings us back to the law of diminishing returns. If we have too much fertilizer, we've applied too much nitrogen, and we get a decrease in yield because the plant can't continue to take that up, or if it takes it up too much, then it will cause some, whether it be a toxicity or it will have some negative effect on the production of that plant. We will not get the benefit or the return on investment for over-applying nutrients. Very simple and very kind of similar nutrient cycle that we're used to seeing. We're going to have plant uptake. We've got mineralization and demobilization, and then those primary and secondary minerals are going to release these micronutrients into the soil, and the plant can then take them up. If you remove the crop residue, those micronutrients don't get added back to the soil. So this is also another reason why it's important to make sure you leave your crop residues on your field. They will eventually decompose and release these minerals back into the environment. Some of the factors that are going to influence that are basically the same things that have influenced all of our cations. Soil pH is huge. Understanding what reactions are going to happen. Understanding that when you change the pH, you might get some chlorosis, such as in soybean, where you would have iron chlorosis because the iron is not available to the plant because the pH is so high. Organic matter, because that contains more sites for these micronutrients to be adsorbed to or held on to so the plant can take that up. And then we need to be thinking about our mycorrhiza in order to kind of increase the ability to take those nutrients up. And so one of the last things that we want to talk about for these micronutrients is this thing called chelated. You will likely buy your micronutrients in a chelated form, such that there's this complex molecule, this EDTA, that holds on to this iron or copper or zinc or boron or nickel, whatever it is that you need. You will get this in a chelated form, and what this does is it kind of holds that there. So that's kind of chelate is Greek for claw. So it holds it there such that as this EDTA starts to decompose or break down, as the microbes use that EDTA, there's an opportunity for the plant to then absorb that iron or that zinc before it gets adsorbed to the soil colloid. So that's kind of the important thing for micronutrients. Get back. All right, so that ends module 3.3.2. You can now complete quiz 3.3, and this actually ends the course. This is it. That's done. And so if you continue on, you would take soil fertility with me, and we would pick back up with kind of going a little more in depth with these nutrient cycles, and then kind of going more in depth as to what influences these different transformations and how that impacts not only our plant production but also our environmental stewardship.